In this first problem, we're looking at melting a humongous iceberg. Okay, 1 million metric tons. And we're not given a lot of information, but we know that it takes energy to melt ice and turn it into liquid water. And the amount of energy is given here is the delta H, which is the change in enthalpy, is equal to 6.01 kilojoules per mole. So really this problem is about converting, the hardest part of this problem is converting your mass of water over to the number of moles of water. So the first step on this, I'm going to say, all right, we've got 1 million metric tons. So that's 1 million metric tons, and that is equal to 1,000 kilograms. So 1 million, 1 times 10 to the 6th metric tons. 1 times 10 to 6 metric tons, and we want to change that over. We got to get that over into grams per mole for the water. So that's metric tons, and we will know here it says a metric ton is 1,000 kilograms. So metric ton, 1 metric ton is 1,000 kilograms. All right, so that math would be pretty easy to work. And then we need to go from kilograms to grams. And it is 1 kilogram is 1,000 grams. And that would tell us how many grams of water. And we're not going to stop with grams of water. We got to change that to moles of water. But this part should be pretty straightforward. We got 1 times 10 to the 6th times 1,000, which would create 10 to the 9th, times another 1,000 would be 10 to the 12th. So we've got 10 to the 12th grams of water. All right, so now we have a mass of water. Anytime you have the mass of something, to convert it into the number of moles, what do? We divide by the gram formula mass. So we have 10 to the 12th grams of water. And we're going to multiply that by the gram formula mass of water. Now, let's recap, make sure we all remember how we get that number. We would say, all right, we have H2O, which is 2 hydrogens, and it is 1 oxygen. And hydrogen has a mass of 1.01 grams per mole. I know, it's been a while since we did this, isn't it? And oxygen has a mass of 16.00 grams per mole. And so we'll wind up with 2.02. And then we're going to add to that 16, and we'll get 18.02 grams per mole for water. So if we have 10 to the 12th grams, which is really big, of water, we would take that and we would put our 18.02 grams of water for every 1 mole of water. We do the math on that. Let me punch that in the calculator here. Let's see. 10 times, let's see, 10 to the 12th. All right. Divided by, I know I'm doing this slowly because I'm doing this on my computer instead of a calculator. 18.02. And I'm going to get 5.55 times 10 to the 6th, 10 to the 10th moles of water. All right, so now I have the moles of water. The problem gave us this information up here. The delta H is 6.01 kilojoules per mole. Well, here's our number of moles. So now it's just a matter of 5.55 times 10 to the 10th moles of water. We'd multiply that by 6.01 kilojoules per mole. And that would give us the total number of kilojoules. And when we get the math on that, will come out to be, let me punch that in, 3.34 times 10 to the 11th kilojoules. needed. So that's how much heat would have to be put into that iceberg in order to melt it. That would be the combustion of 68,000 barrels of oil, about 15,000 tons of coal, or 1.1 times 10 to the 8 kilowatts of electricity, kilowatt hours of electricity. So that's a whole lot of heat that's required. Otherwise, you could just let it sit in the sun, but sitting in the sun and letting that melt, it's still going to take a long time. So it's relatively not feasible. Let's go to the next problem. Next problem said if 17.3 grams of powdered aluminum is allowed to react with excess iron oxide, how much heat is produced? Well, if you remember from the previous section, this is the thermite reaction. It gives off a lot of heat. It's very hot. So we need to write out the full balanced equation. So we've got aluminum, which is a solid, and we're going to react that with iron 3, Fe2O3 oxide, that's iron 3 oxide, and then that's going to give us iron. Like I said, this is the thermite reaction. You can look that back up on the previous sections. And then we're going to get aluminum oxide, Al2O3, which is also a solid. And it also gives us, what's the other product from their equation in the part above it? It says it's going to give us 851.5 kilojoules of heat. Now the reaction is going to give us that. We need to balance the reaction so we can do all the math, but that's what the reaction is going to give us. Well, the reaction's already previously balanced before, so we put a 2 there, put a 2 there. I believe that's all we need. Yep, that's all we need. So the question says we have 17.3 grams of aluminum. And it's the limiting reactant because it says we have excess iron 3 oxide. I'm going to, let's see, that's grams of aluminum. Wow, I did it again. I'm pretty bad at forgetting to put my units in here. I think it's being out for spring break for 2 weeks. Probably what's doing it to me. So I have grams of aluminum, so we'll put grams of aluminum on the bottom. What's a gram formula mass? Hey Siri, what's a gram formula mass of aluminum? See, I think it's 27, but I want to say it's 27.1.
The answer I found is 26.98 to atomic mass units.
Okay, so it's 27.0 grams of aluminum. And that's in 1 mole of aluminum. From here, that gives us moles of aluminum. Are there any further steps to this? Well, there are actually, because we have, no, hold on a second. Are there any further steps to that? No, because that gives us the total number of moles of aluminum. So we don't have to do any further steps with that. So I'll take that out. So I get 17.3. Let me calculate that. 17.3 divided by 27.0. And we'll get 0.637 moles of aluminum. All right. So we know from this reaction here that when we have it exactly balanced, that we have 2 moles of aluminum, and we get, what, I think I wrote number 851. I wrote 811. 851.5 kilojoules. So we have 851.5 kilojoules for every 2 moles of aluminum. But instead of 2 moles of aluminum, we have 0.637 moles of aluminum. And so our question is, how much heat? How many kilojoules? So you just do, this is just a, set up a ratio for this. And then we will take this number over here. We'll take 851.5 kilojoules divided by 2 moles of aluminum. Multiply both sides by the denominator there. So that's going to be times 0.637 moles of aluminum. And then on the other side, when we multiply this by the denominator, it gets rid of it. So that gives us the question mark of kilojoules, how much heat. So let me do the math on that. Probably would be easier for me if I had a calculator in here, but I don't have one. 0.5 divided by 2 moles times 0.637. And I get, this math winds up being 271 kilojoules. Equal to the number of kilojoules. So that's our answer on there. And that's how simple that is.